All right, so if we move into our section on the discussions of column dimensions and things that you can expect to see when you begin changing column length, for instance, the obvious change that you're going to see in increasing the column length is an increase in resolution. I think most of us are probably very familiar with that. However, we're also probably aware that it's not a direct one-to-one proportionality, meaning that if you increase the column length by twofold, you will not see a twofold increase in the resolution. Instead, the resolution increases by the square root of n, where n is the number of theoretical plates. And so if we look at the resolution equation here, that's pretty well laid out. So if you increase the column length by twofold, you should, in theory, see an increase in the number of theoretical plates by 2 as well. So number of theoretical plates is directly related to the column length. In theory, I said, in practice, that's not always the case, although it is usually very close to that. So if we increase the column length by 2 and therefore increase the number of theoretical plates by 2, we should see an increase in resolution by the square root of 2, or 1.4 in this case. And if we increase it by 3, we should see an increase in resolution of 1.7. If we look at an actual separation to kind of prove that out, this is a separation on ChiroPac IC3. In green here is a separation on a 50 millimeter length column, and the resolution was 1.33. If we increase the length by 3 to a 150 millimeter length column, and we calculate the resolution is 2.29, which is not quite 1.7, it's actually slightly higher. But as I pointed out, in theory, you will see a 1.7 fold increase in resolution, but there is some variability, obviously, in moving to a different column. The number of theoretical plates is not going to be exactly 3 times more. There's always going to be slight variability in the conditions when you actually run it, temperature, and so forth, things that can ultimately affect slightly the resolution. But the point of this example is to show that the rule more or less holds true in practice as well as in theory. What about the retention time? Obviously, if you increase the column length, you should expect to see an increase in the retention time. And in this case, it is one-to-one proportional. So if you were to increase your column length by threefold, you should expect to see an increase in the retention time of threefold as well, assuming, of course, that all other conditions remain the same, such as flow rate, temperature, mobile phase composition, etc. Now, if we go back and we look at that example again of the separation on ChiroPac IC, you can kind of estimate well from these chromatograms what the T1 and T2 of the peaks are, but I broke them out into a separate table to make the visualization a little easier. So you'll see here for the 50 millimeter length column, T1 is roughly 1.3 minutes and T2 is roughly 1.5 minutes. If you bump it up to the 150, then you do see actually a straightforward threefold increase in the retention time, slightly off for T2, but again, that's kind of potentially coming from differences in the column packing and the effect that the resolution has on the overall separation. So what does changing the column length not affect? So changing the column length, increasing it, does not affect the retention factor or the capacity factor. The retention factor is a measure of how retained a compound is on the column, as shown by this equation here, where K, the retention factor, is equal to TR, the retention time of the peak, minus the T0, or the dead volume, the unretained volume on the column, divided by T0. And so although you are increasing the column length, and therefore you're also increasing the analyte retention time, the column void volume is also increasing proportionally. So if we go and we look at the actual void time or the void volume of a given column for a 50 millimeter length column flowing at 1 milliminute, that time is approximately 0.55 minutes. And for a 150 millimeter length column, that's somewhere in the neighborhood of 1.6 minutes. So if we go and we plug those numbers into our equation for K, and we use the TRs from the previous chromatogram, you see here that for the most part, K1 and K2 are roughly the same between the two columns. There's, again, some slight variation, partially in my estimations of the retention times, and also, again, coming from the slight differences in the variations in the column packing and so forth. But the proof is, in theory and in practice, that they're roughly the same, at least close enough to where you can't say that there's a significant enough difference. What else does changing column length not affect? It does not affect the selectivity. Selectivity is a measure of a system, in our case, a chromatographic system, to distinguish between enantiomers. And as you can see, the equation here for alpha for selectivity is essentially just the ratio of the retention factors. And so because selectivity is a ratio of retention factors, it should be similar. It should not be changing as you increase the column length. So to prove that out, here is that same example again, and calculating the alpha values based on the previous table. You see here that, again, the alpha values are very close to each other, differences arising from differences in column packing and so forth. Now, if we move on from column length to column inner diameter, there's a number of things that we can expect to see, assuming that we keep the flow rate constant. If we go from a 4.6 to a 3 to a 2.1, flow rate remains at 1 milliminute, for instance. Decreasing the column ID will obviously increase the column back pressure. It will increase the peak height, will decrease the column loading, the retention time, and solvent use. Now, I have a little bit of a caveat to that because, again, I said this is assuming the flow rate stays the same, but in practice, we oftentimes will scale the flow rate in order to equalize the pressure, and we'll discuss that a little bit later on. But for now, imagine a scenario where the flow rate stays the same across these different IDs. So if we look just at column pressure, decreasing the column ID will increase the column pressure, again, assuming everything stays the same. If we look at our equation for change in pressure in the chromatographic system, it is directly related to the viscosity, the flow rate, and the length, and inversely proportional to the specific permeability, the particle diameter, and for our current topic, the column radius. So obviously increasing the a decrease in the column radius or the column diameter will increase the pressure. So if we assume, again, that flow rate is 1 milliminute for all of these three analytical ID columns, same particle size, same mobile phase composition, same column length, what we would expect to see is an increase in the pressure of the equation that I have shown here, where radius 1 divided by radius 2 squared should give you the rough estimation or translation of what the new pressure would be on the new column. Now, because of some pressure limitations, not only with the columns, but with the systems, not all of this data was actually gathered in the lab, but for instructive purposes, you can see basically what you would see if you were able to achieve this, looking just at your 4.6 millimeter ID columns on a 50 millimeter length. Estimation at 30 bar, you would see 71 bar and 144 bar on the same length, but a decrease in the column inner diameter, and so forth down the line here. Now, I talked about scaling before, because if you see here, especially this corner, you're starting to achieve pressures that are not only incompatible with the column, but incompatible with most HPL systems as well. So in order to counteract that, like I said, what we often practice is flow rate scaling. So flow rate can be scaled to equalize the pressure, and to do so for a 4.6 millimeter ID column flowing at 1 milliminute, the corresponding flow rate for a 3 millimeter ID column would be approximately 0.43 mils a minute, and for a 2.1 millimeter ID column, roughly 0.21 mils a minute. Now, equalizing the flow rate is going to have some other effects down the line. Obviously, your retention times are going to be more or less the same, solvent use and things like that. So if we go back to keeping everything the same, and we look at keeping the flow rate the same, If we move into those narrower bore columns, going from 4.6 to 2.1, for instance, all of these columns have obviously a smaller inner column volume, and therefore will experience less column broadening. So as the analyte is moving through the column, less space for diffusion, and therefore as the peaks are coming out of the column and into the detector, they will appear sharper as a result of that decrease in diffusion. This can be particularly helpful when you have methods that require high sensitivity to especially low level impurities. So for instance, if you're trying to quantify a 0.01% impurity and it's eluting late on the tail of your major impurity, it's certainly beneficial to ensure that the peak height is relatively high and not diffuse. It makes it easier to do your quantifying than it would be if obviously things were broadened out or starting to tail or co-elute into the peak that was coming before it. If we, again, make sure that we keep the flow rate the same and we're just decreasing the column ID, we will expect to see a decrease column loading, decrease in retention time, and a decrease in solvent use as well. So decreasing the inner column volume means there's going to be less volume for packing material. And because there's less packing material, basically it's easier to overwhelm the selector sites. So you need to inject less sample, which can be helpful, obviously, if you are trying to conserve a valuable, precious sample, but less sample needed, either a smaller injection volume or a lower concentration in order to maintain the performance. Retention is decreased if the flow rate is maintained, meaning if you have a 4.6 millimeter ID column at 1 milliminute and you flow it on a 3 millimeter column at 1 milliminute, you will have obviously less retention. But it will be equalized, as I mentioned before, if the flow rates are scaled proportionally, or at least close to being equalized. And then there's a decrease in inner column volume by going to those smaller ID columns. And if you're reducing the flow rate at the same time, you're obviously going to be using less solvent. So for screening, for separations that involve harsher, environmentally unfriendly solvents like dichloromethane or chloroform, this obviously gives a little bit of an advantage in that regard.